Here's a differential problem, which is given a cubic box 10 foot on a side made of 1/2 inch steel. How many cubic feet of steel are in the shell of the box? One way to look at this is the box is made out of 6 rectangular solid pieces of steel, each of which has a given volume, and then you could multiply that by 6 and you would have the volume of the steel in the box. Another way to look at it is you have a 10 foot by 10 foot by 10 foot cube of air, which you're going to slap a 1/2 inch plate of steel on all 6 sides. So you could look at it in terms of the volume of the box that is 10 foot 1 inch on a side, the cubic box. Take away the inside cubic box, which is 10 foot on a side, which is taken out because it's just air. The simplest way to do this is to look at this in the differential sense. So differential wise, the volume is 3s squared, and therefore dV ds would be 3s squared, or dV is 3s squared ds. And here's the 3, there's the side squared, which is 10 squared, and there's the 1/12, which is the 1/2 inch of steel on each side that makes the side of the box 10 foot 1 inch. And dV comes out to be 25 cubic feet. It turns out that's very close to the correct answer, or the exact answer. So let's look at this in more detail on this mathematical worksheet. Here's the picture of the box, 10 foot on a side made out of 1/2 inch steel. There's the equation for the volume of the box, s cubed. And we're going to estimate that volume 2 ways. We've already looked somewhat at the differential estimate. Here's the incremental estimate. The increment is based upon the actual calculation of the outside box minus the inside box. So looking at this as the increment, which is delta V, the outside box is s plus delta s on a side, which is 10 plus 1 inch because there's 1/2 inch steel on both sides. So this would be 10 plus 1/12 cubed minus 10 cubed. If you had to do this over and over again, maybe you would prefer to expand this and rewrite it in terms of other values, or not. You can also just calculate it as 10 plus 1/12 cubed minus 10 cubed, and the result being 25.21. If you remember before, with the differential estimate, it came out to be 25 exactly, which is a bit low. So just take a look at the difference between, well, even if you look at just the simple calculation here, which would you rather do by hand? 10 plus 1/12 cubed minus 10 to the third, or 3 times 10 squared times 1/12. There's no contest there, really. This would be a very tedious calculation by hand, and this is a very simple back of the envelope calculation to estimate the volume of steel in that steel box. So just because it would take you a long time to do this, you could do this fairly rapidly on your calculator with the cubing, but you could do this one faster. So no matter where you take this, the differential estimate is always going to be faster but less accurate than the actual calculation. And again, this comes into the real-time aspect of this. You can do this very rapidly. This you can do, but it would take, even with a microprocessor, it would take a lot longer than simply the 3 multiplies that are going on here. So let's take a look at how to do this mathematica-wise. So you would define your volume function, s cubed, and we want to get a graphical point of view on this. So here's the plot of Vs, and here's and that plot's suppressed, and S naught is 10, which is the nominal length of the box, and then delta S is 1/12, which is the half inch of steel on both sides, 1/12 of a foot. And this is the graph of the two different volumes. The volume, and you can see the 2 points are very close together here. There are 2 points here, and one represents the nominal 1000 by 1000, 10 by 10 by 10, which is 1000 volume, and the other one is 10 to 1/12 cubed, which is slightly bigger than that. The difference between those two is the volume of the steel in the box exactly. It's the outside box minus the inside box. And here's that calculation. Delta V is the volume of the outside box minus the volume of the inside box. That's the difference between the outside box and the inside box, which is the volume of the steel from which the hollow box is built. Here's a little bit closer look at that, zoomed in. Here's the 0.10 1000 on the curve, and here's the 0.10 1/12, and 1025.21. This is the nominal inside volume, and this is the volume of the big cube, and when you subtract the two you get the 25.21, and that's the delta V. That's the exact value of the cubic feet of steel in the box. Here's the differential estimate. We don't really need the linearization here, although, so we can draw the pictures, write the linearization. The linearization with respect to S is the usual, y naught plus the slope times x minus x naught, but using V and S. Okay, so we're going to, here's the suppressed plot of the blue line, which will go on top of the original black plot. And also we're plotting the plot from above, which put the 2 points on the line. So this is the graph zoomed in of the nominal, where this is 1000 cubic feet for the value of the volume, and this is the 1025 and some change estimate. And you can see why the estimate is so close, because essentially the tangent line and the curve itself are nearly identical. That's because, relatively speaking, we didn't go very far at all from the 10-foot point. 10 foot plus 1/12 is not very far away from 10 foot, and therefore the curve looks a whole lot like the tangent line. So dV is dVds times delta S, and it's 25. The error in the volume estimate, that is, how much are we missing, how much steel is in the box? Well, we're a little bit low. We're a little bit low by approximately 0.2 cubic feet, which is not very much in the face of the, over 1,000 cubic feet of stuff that we've got. How much in error are we? Well, relative to the actual value, we're only about 0.8% too low in our estimate of the amount of steel in the box. And here's a note to the reader. The errors that I'm talking about up here are not the same errors that the book mentions when they're talking about manufacturing tolerances on an entire object. This is the error due to estimating with the increment, or the differential rather than the increment.